Hello friend, welcome to this lecture. In this lecture we start with the discussion of dynamical system. So, let us discuss what is we are going to discuss. So, first let us define what is known as system. So, a system is defined as a collection, set or arrangement of objects. Basically it is either collection of objects, set of objects or arrangement of objects in a way that they are related to each other by interactions and produce various outputs in response to different inputs. So, if we have say some objects, they are collected or they are arranged in a way that they are interrelated and they produce different outputs corresponding to different inputs, we call that kind of arrangement as a system. And a system is called dynamical system if it varies with respect to time t. So, for example, you take electromechanical machines such that motor car, aircraft, washing machine, all these kind of electromechanical machines are coming in under this dynamical system, and biological systems such as human body and the body of different species, they are all coming in dynamical system. And economic structure of countries or regions. So, if you consider any country and consider the economic structure of that country, then it become a system which varies with respect to time t, and we call the structure as a dynamical system structure. And in fact, anything that evolves over time can be thought of as a dynamical system. So, any system which evolves over time, we call that as a dynamical system. And if we model that dynamical system in terms of mathematical model, then generally a dynamical system is described by an initial value problem of differential equation. So, in this particular lecture we focus on concept related to initial value problem, what is initial value problem, what is differential equation, and try to see certain example of dynamical system at the end. So, let us start with the history of differential equation. So, the history of differential equation began in the 17th century when Newton, Leibniz and Bernoulli's brothers solve some differential equation of first and second order arising from mechanics and geometry. So, in the beginning all these problems are started with a problem of mechanics or problem of geometry, and they try to solve these problems using geometrical tools and all that, and in the process they try to solve some first and second order differential equation. Now, differential equation are used to express many general law of nature and have many application in physical, biological, social, economical and other dynamical system. And in particular we can consider the origin of differential equation as the effort of Newton to illustrate the motion of particle, and these equation may provide many useful information about the system if the equation were formed incorporating the various important factor of the system. So, if you consider a real world problem and then you consider the change in some kind of dependent variable, and that dependent variable, if it is a very important factor of the dynamical system, then by looking at the dynamical system, by solving the dynamical system, we are able to predict the behavior of the dependent variable which plays a very vital role in that particular dynamical system. So, let us say that a differential equation is a relation between independent variables. So, most of the time when you deal with the dynamical system and when you rewrite in terms of mathematical terms, it turns out to be a differential equation. So, most often it is coming out to be a ordinary differential equation. So, here we will focus in this lecture and in the subsequent lectures also we will focus on dynamical system as a differential equation. So, here let us start with what we call as a differential equation. So, a differential equation is a relation between independent variable, dependent variable and its first or higher order derivatives. And depending on the number of independent variable, we may classify the differential equation into two parts. First one is ordinary differential equation, second one is partial differential equation. So, in ordinary differential equation, the number of independent variable is only 1, and in partial differential equation the number of independent variable is 2 or more than 2. So, he will focus on ordinary differential equation. So, let yt define a function of t on interval I, where I is some non-trivial interval starting from a to b, where b is bigger than a. Now, by an ordinary differential equation we define an equation involving t, yt and its one or more higher derivatives. So, any equation which involves the independent variable, dependent variable and its derivative, say at least one derivative or say more than one derivative, which may be first or higher order derivatives, and that we call as that equation we call as differential equation. So, here are some example of ordinary differential equation. First one is dy by dt equal to alpha y, where alpha is some positive constant, and d2y by dt square equal to g is some constant, and dy by dt equal to alpha y minus beta y square, where alpha comma beta are some positive constant, and fourth one is m d2y by dt square equal to mg minus alpha dy by dt. So, these are some very trivial example of ordinary differential equation, and in fact all these example have some originated from some real world problem. For example, the first problem dy by dt equal to alpha y is basically represent a very simple example of population dynamics, where this yt represent the population of a given species at time t, and this simply says that when there is no interaction with the environment, then the population growth or can be given by this equation dy by dt equal to alpha y. And if you look at the second equation is basically representing the free fall of a particle from a height, some height. So, it means that when your particle is say falling under the influence of gravity and there is no other say friction or there is no other hindrance, then the motion of the particle can be modeled by this equation d2y by dt square equal to g. Now, if you look at the equation number 3, then equation number 3 is a slight modification of the equation differential equation given in 1, where we have considered one additional term, that is beta y square, and we will see why this beta y square is given. So, this is a say modification of simple population model, and this model is also known as logistic model. We will discuss more about this model further time of duration. And the fourth is m d2y by dt square equal to mg minus alpha dy by dt. If you look at in this, if alpha is equal to 0, then it reduces to the differential equation given in 2, and if alpha is non-zero, then it will turn out to be this. In fact, it is representing the same motion of a particle falling from some height. The only thing is that now we are also considering that there is some kind of resistance due to air, and that resistance is proportional to the velocity of the particle. So, here resistance means it is negating the motion of the particle. So, in that case your motion of particle can be given as m d2y by dt square equal to mg minus alpha dy by dt. Here g represent the gravitational force. So, in second and fourth your g represent the gravitational force. So, it means that fourth is the representing the differential equation which represent the motion of particle when there is some kind of resistance due to air. So, these are some simple example of ordinary differential equation. Now, we define certain basic things so that we can discuss more about differential equations. So, first important part is the order of a differential equation. So, what is order of a differential equation? Order of a differential equation is the order of the highest order derivative present in the equation. So, you consider equation and look at the highest order present in that particular equation, that is considered to be the order of the differential equation. For example, in the first the highest order derivative present is only one, that is dy by dt. So, this is first order differential equation. Similarly, this equation number 30 is also first order differential equation, while as your equation number 4 and 5 equation number 4 and 2, there are two derivatives present, one is dy by dt, another one is d2y by dt, and the highest order is d2y by dt. So, it means that here the second order derivative is present. So, the order of the differential equation is coming out to be 2. So, it means that equation number 2 and equation number 4 is an example of second order ordinary differential equation, whereas this equation number 1 and 3 is an example of first order differential equation. So, first we try to know what is order of a differential equation, then look at the basic concept of ordinary differential equation. So, as we have already discussed that an ordinary differential equation of nth order is defined as a relation, an equation between t independent variable, y dependent variable and its higher order derivatives, one or more higher order derivatives. So, any relation between t, y dash up to yn equal to 0, this is known as ordinary differential equation, and the highest order present is given here yn. So, this is an example of nth order ordinary differential equation, because number of independent variable is only 1, that is t here. So, here this yi where I is running from 1 to n represent the ith derivative of the unknown function y, and here f is defined in some subset of R n plus 2 here, and provides a relation between the n plus 2th variable, that is t y y dash t up to y and t. So, basically this one represent the nth order ordinary differential equation, but there is a small thing we need to consider here, that here this function f may be a implicit function of t, y and y dash. So, here equation 1 may represent a collection of differential equation rather than a single differential equation. So, here because of it may happen that your function f is defined in implicit manner, then this equation number 1 may represent more than one differential equation at a time. In fact, here in this particular thing here, y is representing a scalar valued function. So, consider the following differential equation: y dash cube minus 3t square y dash square plus 3y y dash equal to 0. If you look at this as a equation, this is a relation between t, y. So, t here y dash and yeah. So, basically it is a relation between t, y and y dash. So, I can call this as a differential equation, but here you can see that here y dash, this is an implicit differential equation in terms of implicit relation between t, y and y dash. So, what we try to do here, we try to see that this actually represent more than one ordinary differential equation. If you simplify this further, then I can write this as y dash cube minus 3t square y dash square plus y dash. We can take out this y dash common. So, y dash equal into this thing, that is y dash square minus 3t square y dash plus 3y equal to 0. So, I can write this as y dash equal to 0 or y dash equal to 3t square plus minus under root 9t to power 4 minus 12y divided by 2. So, basically this simple one ordinary differential equation may give rise to your 3 different ordinary differential equation. So, here rather than considering this kind of a relation, we assume that to avoid the ambiguity, we assume that the given differential equation is solvable in terms of the highest order derivative. So, highest order derivative is here in this y dash. So, it means that if it is solvable in terms of the highest order derivative, then we can rewrite the equation number 1 as in this manner, that is yn equal to g t y y dash up to yn minus 1. So, here this in this way we say that if y is a scalar valued function, then this will represent a single ordinary differential equation, rather than considering the multiple ordinary differential equation as a one group. We consider the normal form or canonical form, and from now onward we assume that whenever we talk about ordinary differential equation, we are talking about the ordinary differential equation given in terms of normal form or canonical form. So, it means that your differential equation is soluble in terms of the highest order derivative and given and assuming the form given in 2. Now, consider once we know what is a differential equation, then we try to know what is the solution of the differential equation. So, we define solution of the differential equation as follows: a function phi t is called a solution of equation number 2 given in normal form on an interval I, which is given as a comma b, where b is bigger than a, and if it satisfies the following condition, that phi t is defined on this interval and it should be n times differentiable on this interval I. And second thing, that phi t satisfies the equation 2 for each t equal to I. So, if we are able to find out such a function, we call such a function as a solution of the differential equation given in normal form, that is this kind of form. So, this is the definition of solution of the differential equation, and we in all the problems we are trying to find out the differential solution of the differential equation in defined in terms of this definition. So, the aim of the study of the ordinary differential equation is to find the unknown function represented in an explicit form, that is it should be that y is defined in terms of t using some elementary functions. So, what are elementary functions? Some example of elementary functions are these sine function, trigonometric functions, polynomials and logarithmic functions. So, it means that our primary aim is to represent yt in terms of t in terms of elementary using elementary functions, and in the absence of an explicit form, we need to study the behavior of solution by available analytical method. So, in case of when we are not able to find out the solution given in terms of explicit form, we try to focus on the properties of the solution given in terms of implicit form. So, now so we know what is the solution and what is the aim of the study. Now, we to start with the solution procedure, we classify our differential equation. So, the classification is basically based on mainly based on two categories. First is classification based on dependent variables, that is linear or non-linear. So, the classification based on dependent variable gives you a linear differential equation or a non-linear differential equation, and the second one is the classification based on conditions, whether it is initial value problem or say boundary value problem. So, we will discuss one by one what is this classification and how we can classify a given differential equation. So, first consider the differential equation given in normal form, that is yn equal to g t y y dash y up to yn minus 1, and if the relation g, this relation is linear in its argument here is t y yn minus 1, but the linearity or non-linearity will depend on the dependent variable and its derivative. So, if g is linear in y dash up to yn minus 1, then the differential equation 3 is called a linear ordinary differential equation, otherwise it is called a non-linear ordinary differential equation. So, for example, if you look at this y dash plus ky equal to 0, we can see that here your y dash coming in a linear manner. So, we call this a linear differential equation, and whereas the second problem, that is dy by dt equal to y square, here if you look at here y square is not linear, this term y square is not linear. So, we say that it is a non-linear differential equation. If we simply say that linearity means that they present in the equation in a linear manner, in the sense that they have only one power. and the coefficient of y or derivative of y may be only the function of t only, the independent variable. But if you follow this kind of definition, then it is very difficult to check whether this third equation, that is y dash plus modulus of y equal to 0, is a linear or a non-linear differential equation, because here it looks that y and y dash are coming in a linear manner, their power is only 1. So, the procedure that checking that whether the y or the derivatives of y are present in the equation in a linear manner may not give you a proper definition of a linear and non-linear differential equation. So, here to give a proper definition of a linear and non-linear differential equation, we use the concept of operator, and we say that if we define suitably what is the operator based on equation number 3, and if the operator is linear, the corresponding differential equation is also linear. So, let us consider the following differential equation of order 2. So, let us take an example, and we have taken the example of differential equation of order 2 and define Ly as y double dash plus Pty dash plus Qty, and your differential equation is this, that y double dash plus Pty dash plus Qty equal to Rt. So, basically I can write this, that Ly is equal to Rt is your differential equation, and where Ly is defined as this, that Ly equal to y double dash plus Pty dash plus Qty. So, here once operator is defined, now we check whether this operator is a linear operator or not. If you look at here, the notation, this Ly suggests that the operator L operates on a function y and gives this value. So, output is y double dash plus Py dash plus Qy and input is your y. So, basically operator is basically what? An operator L defined on vector space V with the scalar field k to vector space V over k is said to be a linear operator on a vector space V defined on a scalar field k if it satisfies the following equality, that L of alpha x plus beta y equal to alpha times Lx plus beta times Ly, where these xy is coming from vector space and this alpha beta is coming from this scalar field. Then if an operator satisfy these properties given in equation number 4, then we call this operator as a linear operator. And if it is a linear operator and it is associated with differential equation in this way, then this differential equation, that is y double dash plus Pty dash plus Qty equal to Rt, is a linear differential equation. So, here now let us look at here. So, look at this y dash plus mod of y. So, you define Ly as your y dash plus mod of y, and so it is an operator, it takes the input value y and giving the output as y dash plus mod of y, and then now look at the whether it is a linear operator or not. So, look at alpha y1 plus beta y2, and this is what alpha y1 plus beta y2 derivative plus modulus alpha y1 plus beta y2, right. And if you look at alpha of Ly1 plus beta of Ly2, then it will give you alpha y1 dash plus modulus of alpha y1 plus beta times, there is a small problem here, it is here it is alpha is outside. So, here you can write it like this, and beta times y2 dash plus modulus of y2 here, right. So, alpha times Ly1 plus beta times Ly2 is given by this, and you can check that though these terms are same, that if you simplify, this is nothing but alpha y1 dash plus beta y2 dash, but this term is not equal to, so let me write it here. We can, if we simplify this, what you will get, if you simplify, you will get alpha y1 dash plus, here you can get beta y2 dash plus alpha times modulus of y1 plus beta times modulus of y2. So, it means that this term is same as this term, but this term is not equal to modulus of alpha y1 plus beta y2. So, it means that here your operator L defined in this way, y dash plus mod of y, is not a linear operator. So, it means that the differential equation y dash plus mod of y equal to 0 is not a linear differential equation. So, we say that this is an example of a nonlinear differential equation. Similarly, we can consider the other example. For example, let us consider the second example, and here you define Ly as y dash plus ATY. Basically, when we check linearity, we are checking the linearity in terms of dependent variable and its derivative. So, here now we write Ly as y dash plus ATY, and now we check whether this define a linear operator or not. So, you check that alpha y1 plus beta y2 is coming out to be alpha times Ly1 plus beta times Ly2. In fact, this is what? This is alpha y1 plus beta y2 dash plus AT, here it is alpha y1 plus beta y2, and when you simplify you will get alpha y1 dash plus alpha AT y1 plus beta y2 dash plus beta a y2, and this you can write it alpha times L of y1 plus beta times L of y2, that is your right hand side. So, here your Ly defined as y dash plus ATY satisfy the property of linearity. So, we say that this differential equation defined as Ly equal to Bt is a linear differential equation. So, this is the classification based on say a dependent variable, and we say that since this differential equation is linear in terms of dependent variable and its derivatives, we call these kind of differential equation as linear differential equation or nonlinear differential if it satisfies the nonlinearity. Now, let us look at the classification based on the conditions provided with the differential equation. So, consider the following differential equation, y dash t minus alpha y2 equal to 0, t belongs to R. Then this represent the population growth model in a single species as we have pointed out. Now, we may easily find out the solution of this, and our solution is given as y t equal to c e to the power alpha t, because it is the simplest differential equation we have already considered, and here c is an arbitrary constant, and this will act as a solution of the equation given in 5. Now, here if you look at c is an arbitrary constant, so it means that if we vary our c, we will have a different solution of the equation number 5. But our real model problem, basically this equation number 5 is coming through some kind of a real situation. So, it means that we are expecting a unique answer to that particular problem. So, it means that we have to find out, rather than in Feynman-Manis solution, we have to find out the unique solution. So, for that we had to prescribe some kind of condition associated with the differential equation. So, in this case we may provide the conditions in terms of the initial condition. So, it means that frequently we are interested only to find out those solution which also satisfy certain other condition, and such condition may be represented in several forms, but the most important forms are given in terms of initial condition and boundary conditions. Now, we try to understand what is initial condition and what is boundary condition. So, that we can understand with the help of some example. So, first let us consider that we want to find out the population of this species at given time t, provided that the population at time t naught is given by y naught. So, it means the initial condition, the condition associated with the differential equation is given in terms of that at t equal to t naught your population is given as y naught. So, it means that y at t naught is your y naught, and now we want to find out the y population at time t, and we say that if you look at different value of this y naught and t naught, you may have a different solution of the same differential equation. For example, if I take y naught as 0, then we can get c equal to 0. So, if I look at y t is basically what? Y t equal to c e to the power alpha t. So, it means that if I assume that y naught is 0, that is 0 equal to c e to the power alpha t naught, then the only possibility that we will get this equation valid, that c has to be 0, and in this case when the initial population is 0, then y t will remain 0 for all future time t, and if you replace y naught equal to 1 and in this case 1 equal to c e to the power alpha t naught. So, we can find out the value of c, that is coming out to be c equal to e to the power minus alpha t naught, and your population is given as y t equal to e to the power alpha t minus t naught. Now, in case of when t naught is replaced by 0 and y naught is given by some value say y naught, then you can consider we can calculate the value of c as y naught, and your population at time t is given by y t equal to y naught e to the power alpha t. So, here we can say that by defining different condition at time at the initial point, that is t naught, we may have different possibility of solution. So, it means that the defining the condition create a lot of impact on the solution procedure. So, the condition defined at one point or say initial point is known as initial conditions, and the differential equation associated with the different initial conditions is known as initial value problem here. Now, look at the another example. Here we are again considering a very simple example, y double dash plus y equal to 0, which may be considered as a example originated from a motion of simple pendulum, y double dash plus y equal to 0, and if we already know how to solve it, and we can solve this and we can get y t equal to alpha sin t plus beta cos t. By the way, here I am assuming that you know some how to solve some simple ordinary differential equation, for example linear differential equation, exact differential equation, or say reducible to exact differential equation, or higher order equation involving say constant coefficient, that I am assuming that you know. So, here once we know the solution, then if we define conditions, since it is a second order, we need to fix two arbitrary constants, that is alpha and beta. So, we need two conditions. So, let us define conditions as y of 0 equal to 0 and y of pi by 2 equal to 0, and if you do this, you can easily check that your alpha and beta both are coming out to be 0. For example, if y 0 equal to 0, then it is your alpha into 0 plus beta. So, this implies that beta equal to 0. Now, y of pi by 2 0 equal to, this implies that since beta is already 0, so alpha and sine of pi by 2, that is 1. So, this implies that alpha is also 0. So, it means that if we assign these condition, that is y 0 equal to 0 and y pi by 2 equal to 0, then solution is coming out to be y t equal to 0. But if we replace our initial with conditions like this, y 0 equal to 0 and y pi by 2 equal to 1, then your solution is now coming out to be non 0, and it is coming out to be y t equal to sin t. So, look at these two example and look at that in example 1, that is this example. Here your condition is given at point t equal to t naught here, whereas in this example your conditions are given at two different points, that is 0 and pi by 2. So, it means that condition given at the same value of t are known as initial conditions. So, condition given at one point is then known as initial condition, whereas the condition defined at 2, generally it should be the end point of the interval, or more different points are called boundary conditions, right. So, this is the classification based on the conditions associated with the differential equation. So, we know what is differential equation, we know how to define the solution and how to classify the differential equation such as linear, non-linear, initial value problem or boundary value problem. Now, so far we have discussed the classification and definition of differential equation, solution, and the required information related to this differential equation. And in next lecture we will continue from this. So, here we will stop and we will conclude this lecture. Thank you very much for listening us. Thank you.